All right, thanks. So I'm going to be talking about, the title here is Halo Bias Beyond Cold Dark Matter, but I'm happy to be talking to this really expert audience. So just some preliminaries. In this talk, I'm only going to be talking about the really large-scale linear bias, meaning the B1 coefficient of delta, and that's not because I don't think that all of these other k-squared, k, peak constraints, velocity bias, and so on are there, but I think there's something interesting going on already at this level, so I'm just going to focus on that in this talk. And more than that, I said beyond cold dark matter, but I'm actually going to talk about halo bias in cosmologies with cold dark matter and massive neutrinos, where I have perturbations in both. But I think that some of the ideas and some of the things that changed a little bit here could be applicable to more general non-standard cosmologies where you have other things going on. So I will quickly review some of the stuff about the growth of structure in cosmologies with massive neutrinos and cold dark matter, and then a little cartoon discussion of how thinking about halo bias given linear structure formation in neutrino cold dark matter cosmologies, and then an example simple calculation of stuff, and then some implications of the idea. So just as a reminder, if I have cold dark matter and massive neutrinos, the way that the density perturbations grow is different than if I just have cold dark matter, because neutrinos are relativistic for most of the history of the universe and have large velocities which prevent them from clumping. So if I'm looking at a really large scale density perturbation, which is coherent in cold dark matter, baryons, and neutrinos, then all of these overdensities will grow together. The neutrinos don't move very much, and I have the usual growth of structure, ignoring lambda for the moment, where linear perturbations just grow at the scale factor. But if I'm looking on scales which are small compared to the typical distance a neutrino travels in a Hubble time, then the neutrinos will just stream out of the perturbation, leaving the cold dark matter and the baryons behind. And as a consequence, this overdensity in clustering matter grows more slowly than it would have otherwise. And so the neutrino density perturbation on these scales rapidly damps away, and the cold dark matter perturbation grows more slowly with this approximate solution where the power law is a little bit smaller than 1. And so this leads to the usual suppression in the matter power spectrum, where on large scales, at fixed omega matter, the large scale power spectrum is about the same. And on scales below this free streaming scale, the amplitude of clustering is suppressed. And then one thing to just keep in mind is that this suppression changes with time. So it's not, this is at redshift 0, and this is at redshift 1 and 10. And this is because the growth rate of perturbations on this scale is different than the growth rate, the linear growth rate of perturbations on the larger scale. How does that affect halo bias? So I want to think of a really simple cartoon picture of halo formation, where I'm thinking of halo with possibly cold dark matter and neutrinos. But the first point is that neutrinos do not cluster very much in the halo. So to a very good approximation, as also was just shown in Yassine's talk, I can ignore any contribution to the neutrino density. So this is just showing that for reasonable neutrino masses, the contribution of neutrinos to the halo mass is like 10 to the minus 5 or something. And also, they don't really cluster in the halo, and they don't really affect the actual formation of the halo itself. So if I want to think about, this is a plot similarly showing the change to the critical density when I include the clustering of neutrinos within the halo while it's forming. So a simple spherical collapse calculation where I ask whether the gravitational contribution of neutrinos changes the collapse threshold. And the answer is that it's tiny unless you allow for very large neutrino masses, like sterile neutrinos, which are in conflict with data anyways. So the useful thing to write down is just that, so omega neutrino h squared is approximately the sum of the masses over 94 eV, right? And so the upper limits, the current upper limits on the sum of the masses are somewhere between 0.2 to 0.6 eV from cosmology, and from particle physics, the 95% upper limit on the anti-electron neutrino mass is less than 2 eV. So much weaker, but small contribution. So something like 0.5%, a couple percent. Okay, so the point of that was just to say that if I want to think about halo bias, I'm going to ignore the neutrino clustering at the nonlinear level completely, and then just imagine the usual picture of cold dark matter clustering and forming a halo. But the effect of neutrinos is that the background that the halo is forming in is different depending on the scale of the region. So this is a cartoon which is meant to show little halos, which are these pink dots, which live on long wavelength perturbations of different scales. So I'm thinking of halo bias in some kind of peak background split picture where the halos that are forming only care about the local quantities like the matter density and so on. But in the case where I have both neutrino and cold dark matter fluctuations, the evolution of the background density that these halos see is different depending on the scale of the long wavelength perturbation. So if I have cold dark matter perturbations only, then the linear evolution of density perturbations doesn't depend on their wavelength. So if I'm a local halo, I couldn't, and I measure like the density and the rate of change of the density, I couldn't guess the wavelength of the perturbation I'm sitting on. There's no information about scale. But with neutrinos, if you're sitting here, the density, the rate of like dilution of the density is different than it is over here on this longer wavelength perturbation. So there's some local thing which is different between these two cases. And so that should affect halo formations. If I think like, if I start at some early time where I have the same amplitude of density perturbations up here, and that's going to make it easier for these guys to collapse, say, and form halos. If I compare at a late time, the final background density perturbation will be a little bit smaller than it will be here. And so if I'm asking how many extra halos I should have in these different regions, it won't necessarily be some function of just like the final time density. Is that any questions? Okay. Okay, so how much being in this picture, how many more halos you form in overdense regions should depend on the wavelength of the overdensity. And then another point is that if I have multiple fluids around, I need to think about which one I want to use to keep track of mapping between Lagrangian and Eulerian space. This, in principle, I think could be a matter of convention, but if I'm thinking of cold dark matter halos forming from blobs of cold dark matter and these particles having initial velocity at not having any initial velocity with respect to the rest of the cold dark matter, then it's the cold dark matter that you should use to track the increase in halo density in a late time overdense region compared to an average background. So in other words, halos are, if I think of halos as test particles in the overdense regions, then they just follow the same equations as cold dark matter, as Matteo discussed yesterday. And so that would argue that the halo number density should be boosted, the Eulerian number density should be boosted relative to the Lagrangian by 1 plus delta cold dark matter, because the cold dark matter is conserved, not the total matter. But note that if I have multiple tracers of whatever density field, anything that's tracking cold dark matter identically would give you the same result as this. But this is different than putting the total matter there. So that's just some general thoughts about thinking of halo bias. And then so here's some cartoons discussing how halo biasing should be different in a cosmology with cold dark matter and massive neutrinos. And then there are various ways that you could calculate things, but I did one first simplest calculation of how this should look. And that's the following. I just did a spherical collapse calculation asking about how a spherical overdensity of cold dark matter collapses to form a halo in different backgrounds. And this is fine. I can just use the regular equation of motion, acceleration equation for the radius of the proto-halo, but include the background density stuff in other components that aren't cold dark matter and therefore aren't collapsing along with the halo. And I allow these extra components to have long wavelength density perturbations. So in this case, it would be neutrinos. And in fact, everything else that's part of the cosmology. and then modify the initial conditions appropriately as well. And with that, you can calculate how the local collapse threshold, so how large of an initial density perturbation I need to collapse as a function of the adding the long wavelength background perturbation. And then I can just evolve these both to the present time and take the derivative and find how the local collapse threshold is changed by the presence of a long wavelength mode as a function of the scale of that mode. So the normal case is that this derivative of delta critical with respect to long wavelength mode is just -1. And that's indeed what you see on these small scales where the growth rate of small scale perturbations and large scale perturbations is comparable. And on large scales, you see something different. So the effect of having a long wavelength background mode doesn't help you collapse as much as you think it would if that background mode is larger than the free streaming scale.
This is a spherical model.
Yeah.
Can I just mimic the background as a local universe where omega is higher? So then I still can do this completely analytically?
Yeah, so there are two things. Yeah, so there are two things. One thing is that, so you can't quite mimic it as a local universe because energy is not conserved below the neutrino free streaming scale because I have neutrinos streaming in and out of that region. But I could treat this as a local, it's a Newtonian problem, so I could just ask how particles in this background with neutrinos and cold dark matter evolve.
So the gradient in the neutrino perturbation actually play a role in your calculation?
No, not at all. It's treated as completely smooth. Sorry, and I completely forgot to say that this discussion here is very related to work that Ravi's done with Lam and Kyle about scale-dependent growth due to modified gravity, leading to a scale-dependent halo bias at the end of the day. I just meant to mention that. I had it on the slide, but sorry. Yeah.
More? So, well, I should say, if it's just totally smooth, why not just have background? So that's
yeah. So I mean, I just did a really simple calculation, but that's exactly what's in it. That's a Yeah, so if you have, on superhorizon scales, the perturbations are coherent, but below the neutrino free streaming scale, you can tell that they're not, the neutrinos stream out while the cold dark matter collapses a little bit. So you get it. It's anything below the neutrino free streaming scale, it's not you have an extra parameter. The Hubble scale isn't the appropriate scale anymore, but it's,
right. But
yeah.
That's on small scale, where you have streaming and then actually the decay of the potential
Yeah, it's not, but it's on the scales that I care about. So here it's roughly the neutrino free streaming scale that separates these two regimes, but you roughly have a constant -1 on this scale and then something else on this scale. But it's not a separate universe, but you could treat it as a smooth background. Yeah, and I see it not being exactly -1 here, but this is about the precision of my calculation. I mean, the precision of my calculation is not much above this, but because this is not a omega matter equals 1 calculation. It's our universe with all this stuff. Okay, so this gives you a prediction for how the long wavelength density changes the local threshold for collapse, and I could plug that into a calculation of how that changes the linear bias factor. And here, so I guess the thing to keep in mind is that this decreases the bias on large scales relative to small scales. But I've plotted it differently here, just showing the fractional change in the bias. So I've normalized all of these bias factors by the large scale value just to show this fractional difference over here. So what you see is this is a huge range of scales, but again, it's just a kind of simple calculation to illustrate the idea and the size of the effect. And what you see is that there is a constant bias on very large scales, but on scales that are below the free streaming length, I have another constant value, and then there's some transition region between the two. And these vertical lines are the velocity of the neutrino over the Hubble scale at this time. And so you see a scale-dependent change in the bias, and the amplitude of that change increases with neutrino mass, and it's roughly scales as neutrino density over the matter density. So these are very small changes. These are percent level effects, but it's some scale-dependent change due to neutrinos in the linear bias factor. Yeah, actually, so it's really just the bias factor. This isn't. It's PMN. That's right. Yeah. Yeah. So it includes two scale-dependent changes. It includes one change from the collapse threshold changing, and another from the fact that you don't have neutrino perturbations on small scales, and they both work in the same direction. That's right. CDM would be flatter. So, but it would be. So you have. Let's actually see. There. So roughly, the total change in the bias with respect to the total matter, as opposed to just the cold dark matter, is the sum of these two pieces. And this piece is the one that wouldn't be there if you were looking at it compared to CDM. You would not have this F nu. But it depends on what you're measuring. If you're looking at lensing, you'll see both of them. If you're comparing two galaxy populations, you will still see this piece if they have different biases, but not this piece. So that's fine. So it will be smaller. Both of these terms scale with F nu. This one has some numerical factor, which I can't guess, but could only calculate numerically. And then scales as b minus 1 over b. So coming from, roughly scales as b minus 1 over b, coming from the logarithmic derivative of the mass function with respect to the background mode. Yeah? High K? And no, in this one it's not. And so I think the sort of one way that I think about the difference coming is that if the bias is telling me how many extra halos I have in an overdense region, but the way that we usually define it, you're defining that how many extra halos you have in an overdense region with respect to the density today, right, that you see. And if the density perturbations grow at different rates, so they grow faster here than they do here, then your guess of how many more halos you should see is just by evaluating the density at the current time doesn't tell you how boosted your growth was at early times, if that makes sense. That's one.
Is that correct? Just because you change background, compare with that, without that background, of course, then you also change your...
Yeah, halos which live on density perturbations on these scales see a locally different background than these guys do. The growth rate is different.
So there's two scales here, right? One is the mass scale of the halo.
Yeah, which I'm assuming is well below all of these, so I'm not worrying about that, which is fine for 0.05 EV neutrino. And then there's the scale of the free streaming scale. Yeah. 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 So it's not actually for an omega matter equals 1 cosmology that I did this calculation. I did it for our universe, which actually does have other stuff around besides cold dark matter, so it might be because of that. But yeah, this is about. I'm not going to make any strong claims about it because it's tiny and it's about how accurate I trust my code to.
But even for m equals 1, it's not exactly 9. Because a lower density means you're in a curved universe, right? So that does change the collapse. Most people don't think that.
Actually, I think you can write. Well, let's talk about it after because I want to get to the next thing. But I'm not sure if I agree with that. So a quick comment is just that part of this is thinking about, because this is a bias workshop, part of comment for discussion is just thinking about. I guess you could write the effect of a long wavelength mode on the local number density of halos in terms of the value of the density field at the time you observe or something. But in principle, the change in the number of halos depends on like the sum over the whole history of how the long wavelength density mode was evolving. And I think.
Yeah, so if you change the neutrino mass, actually total omega matter also changes. Is that right? You
Yeah, actually, so in my paper, I think I have plots with respect to both fixed omega matter and a fixed omega cold dark matter. I think, yeah, I mean, you have to keep. Yeah, that's right, but it's different than what you see. So the small scale perturbations grow with it. It's different. Yeah, the background is still different. I'm not sure if I'm not understanding your question. Okay, so I'm out of time, but there are two reasons why this is interesting, aside from just thinking about how to calculate bias. And one is that this is a systematic for measuring neutrino masses from galaxy clustering. And number two is that it's actually a signal if I have a really futuristic survey that can actually measure this bias factor. So let me show a couple of plots really quickly. One is that if I was just measuring the matter power spectrum, then I see a suppression, and I want to measure neutrino mass, then there's a suppression in the amount of power at small scales, and that suppression is a measure of the neutrino mass. This is roughly minus 8 f nu, whatever at fixed omega matter equals to 1. Now, if I had constant halo bias, then the suppression in the galaxy power spectrum would be the same as the suppression in the matter power spectrum. But if I have this scale-dependent halo bias, the suppression is weaker. And the amount by which it's weaker depends on the bias of the halo. So this is this b minus 1 over b p f nu plus b minus 1 over b f nu. So that's systematic if I was just using this information to measure neutrino masses. But if I have a really futuristic survey with a huge number density of tracers, I can play these tricks of getting rid of sample variance by looking at the ratio of the biases of two different populations, for instance. So similar to stuff that Urosh has discussed with using the scale dependence of the bias to measure non-Gaussianity. So this is showing the halo bias as a function of scale. If I could measure the absolute halo bias, which of course we can't because we don't have a real independent way of measuring the density field, or the ratio of the biases of two different galaxy populations with a very large number density of tracers. So these numbers are like, this is 5 times 10 to the minus 2 h inverse megaparsecs cubed. And for comparison, if you thought about this before, it's similar to detecting FNL of 1 with scale-dependent bias. So the size of this, that's what these black curves are here, is the scale-dependent bias for FNL of order 1. So if spherics could detect that, then comparable to thinking about this neutrino mass effect. And of course, in the angular, you could also use the angular power spectrum galaxy lensing cross-correlation compared to the galaxy-galaxy autocorrelation. The angular power spectrum.